we are, should I introduce us? I'm Alex.
I'm Tony.
I'm Mark.
Keegan.
And we're working on the controlling the strength of 3D printed parts. And there we go. So our objective here was to focus on making the 3D parts stronger than in current systems. And right now, 3D printing in general has a sort of issue where the strength hasn't been focused on too much, and so a lot of the applications for 3D printing up until now have been either sort of rapid prototyping or sort of non-load-bearing applications where you don't need a lot of strength. And so when we originally started the project, we had a very open-ended situation because I think an earlier project group talked about the fact that there's a whole myriad of different 3D printing technologies. So to sort of give our project a little more focus, we just sort of chose one that seemed to be have a lot of things that we could focus on within it. And so the type we went with is sort of a cheaper 3D printing technology where you have a bed of powder particles that you have a binder material that is deposited into the bed in layers, and at the end of it, the binder material is bound together specific areas in that powder that at the end of it you can just remove the excess powder and recycle it or something for a later 3D print. But you can get a pretty accurate 3D printed part, and it's the advantage of this system over, say, like an extrusion mold where you have plastic being deposited is because it's embedded in a giant bed of powder, it sort of supports itself while it's printing, so it makes that easier. Let's see.
So the patent, sorry. So the patent that we chose was very similar to what we're doing, 3D printing with powder and a binder. So the powder process builds up the part into layers, and an inkjet head places the binder onto selected areas of the powder bed. And the parts that are not selected to receive the binder are still loose powder, and the cleaning takes place after the parts are created fully in their layers, and a brush of some sort is used to get rid of all the loose powder. And to increase the strength, it may be necessary to heat treat the final part. And this increases the strength between the bond between the layers of particles.
Okay, so the existing product we looked at were the Z printers by 3D Systems, and this is one of the bigger commercial powder printing ones out there. And we chose those because they are state-of-the-art, but the issue with them, as Alex touched on before, is the uses of the products are still largely show models, visual displays. They aren't very strong, they can't be used. So despite it being a cheap, quick way to manufacture parts, there's this need for stronger parts to come out of them so we can use the complex geometries we can get easily and kind of open that field up to a lot more uses.
So this shows our upper level decomp. Our FR0 was control strength of the 3D part, and our DP is just a system to control the strength of the 3D part. In the parentheses, we kind of put into just variables and relations between our DPs and our FRs, so you can see it kind of as it goes down throughout the whole entire project and the whole entire decomposition. Our FR1, 2, and 3 are control geometry of the part, control strength of the binder in between the particles, and control the powder particles. This is our FR1 going through just controlling the geometry. Our FR 1.1 is just the distribution of the binder. That's kind of a big thing in this. It has a lot to do with the motion, because this has your X and Y motion, and also you have to deal with the flow rate of the binder coming out of the head, or what's used sometimes is an inkjet. We kind of called it a nozzle, so we didn't limit ourselves. The next is a 1.1, which is distribution of powder, and this our FRs went with the layer thickness, which also involves your strength and how much you actually have a binder can be put into it, and the overall speed of the process.
FR2 gets more into the actual strength of the binder. FR1 was more about the 3D printing process in general, and FR2 is the bonding between the powder particles. So we broke FR2 from the strength of the bonds into controlling the strength of the adhesion between the binder and particles, so how the binder and the particles form together. And then we wanted to control the strength of the binder material itself. So with the adhesion, there were multiple methods. We decided to choose an adhesion mechanism based on, we'll get into that a little bit later, but based on minimum amount of information. I'll just keep on with this right now. All right. And then we also wanted to control the contact area between the binder and particles based on our method of adhesion. The adhesion mechanism that we chose was very similar to the way that Velcro works, where you have two parts that are coming together. One has, I don't even know how to describe it.
Like loops and hooks. Hooks basically just a mechanical interlocking feature.
Right. And then with the binder material, we felt it was important to control the crystallinity because that has a major factor with the strength as well. And then,
So the reason we went with the mechanical adhesion is we looked into the research, and it seemed that mostly if there was a break to occur somewhere, it was going to be between the binder and the particle. So we needed to ensure that we had a good bond there, and how to achieve that adhesion, we went to Axiom 2. So probability of success versus your information content. And what kind of bonds had the most information, what did they had more variables in it, what had more going into it, and we found that mechanical adhesion had the least. We just needed those interlocking features. If we gone with electrostatic or magnetic, we have to look at separation distances. The polarity of the different particles is, do we need to charge the binder? Do we need to charge the powder bed to get them to adhere at the beginning? If we got on something with sintering, the solubility, how many different freedom of movement there are at the polymer level, and things like that. So it looked like the mechanical adhesion was definitely the best way to go, since it had the least information to it and the greatest probability of success.
our FR3 was controlling the strength of the powder particles themselves, and this we mainly focused on the grain size, and based on the grain size, we wanted to control our cooling rate, and that was, well, our grain size strength was based on the Hall-Petch constants, and the cooling rate was based on a TTT diagram based on the material selection.
So, we sort of have a lot going on here. We did go through a couple iterations where we found that a few things were coupled, and so for this version we think we've gotten everything uncoupled, as it's shown pretty clean matrix. A lot of the reasoning behind it being uncoupled is, well, just first of all, the FR1, 2, and 3 sort of happen at different, completely separate areas. So the chemistry related to bonds and the chemical makeup of the powder would happen outside the machine, which is what's FR1 is dealing with just inside the machine. So that just inherently is very uncoupled. And then within each of those, we sort of looked and made sure that different things that were happening, like isolating X position of the head and Y position of the head, weren't interfering with each other. I guess I compressed them here, but underneath each of those is just sort of describing how X and Y are achieved. But okay, so there's that for the functional and design parameters. And then what we also did is looked at a physical integration matrix, which is similar, but for this one we have, we're looking at a lot of the DPs and how they relate to each other. So we wanted to make sure, for example, that when we're distributing the powder or distributing the binder, that those processes aren't getting in the way of each other. So we went through and looked at that and made sure that none of those were coupled. And anything more? Next.
So going through it all, we basically found that 3D printing, as far as the mechanics of it, the XY position, the powder bed, that's been figured out pretty well. And the most amount of improvement, at least as far as strength, which is what we were looking at, is going to come from the materials. And looking at Axiom 2, that mechanical adhesion is probably the best bet for that. So we know how to do the mechanics of it, but increasing the strength is going to come out of controlling what powder you're using, what binder you're using, and making sure you get a good, strong mechanical adhesion out of the two. So thank you, everybody, for your attention.
Questions? Comments?
Can you go back to the decomposition that talks about the TTT diagrams? I was wondering how that helps to control the plastic strength, how that works.
Okay, so the question was how looking at the TTT diagram would help control the plastic strength of the material.
For our powder particles, we're actually looking at more of a ceramic type material.
Yeah, I just looked at TTT diagrams for alloys and
No, for
ceramic.
As long as we're here, there was a refinement we discussed that you guys didn't pick up on. I'm not sure why. But,
Yeah, we were about getting rid of this.
well, so one of the things is the parent is control strength. Right now, the link between grain size and strength, which is great, and I'm glad you guys showed this. By the way, this is a positive point. I'm trying to speak loudly myself to get this up. So you're showing the relationship, for example, the Hall-Pesch relationship here, and I think more people could be doing that. You don't have to do it throughout the matrix, but being able to show how you transform a DP to an FR or a PV to a DP, that's important. And so it would be good to show that relationship and how that transfer is made. And then you can see where other things come into this. Now, so this is nicely broken down here. The only sort of little wording change I might make is that there's control strength. It would be nice to say control strength through grain size, control strength. And,
We actually did that originally, and then we took out control it through, because then for every other in our FR2, we were controlling the strength through this, controlling the strength through that. So it seemed kind of we were trying to apply it to everything, and we weren't sure exactly if we should be applying it to everything.
Right. At some point, it seemed like we were kind of predicting the DPs because we'd have control strength through something, and then the DP would kind of fall into that.
right, and this is one of these things where maybe you needed another domain
Mm-hmm.
and to get to the process domain. But I think the intent is clear, and so just a comment about, we want it to be clear that the children are the children of the parent, and this is controlling strength. So I think we could say, geez, if we were really being formal on this, maybe we need another domain, maybe we need to do that, but I think we've done a nice